Hello everyone, so welcome back to another video on concurrent assertions, and this time also we are going to practice few basic examples, and then on the next video we are going to discuss some new things on concurrent assertions, just like we did during our previous video, like the implication operators. So let's begin. So our first example of this video is going to be very simple, and it says that at the same edge of the clock, suppose there are two signals A and B, and at the same edge of the clock, or the posage of the clock, let's say we want to be more specific. At the same posage of the clock, both A and B can't be true. So which basically means that A and B cannot be asserted at the same time. So we are going to begin with our property. So like I have discussed in my previous video, you could just uh, write the property and sequence separately, but there are certain limitations in sequence, such as you cannot use the implication operators. So for that reason, I will mostly prefer writing the sequence directly inside the property. So I will name this property A underscore B uh, not same. It's a silly name, and you could just name it whatever you want. Underscore P, which signifies that it's a property. So here I want my property to be sampled at every posage of clock. So at every posage of clock signal, both A and B cannot be true. So here what I will do, I will use the simple logical operators, and between A and B, I will use the conditional operator. So this basically means that A and B cannot be true at the same edge of the clock. So this concludes our property. So let's assert this, and I will give it a label. And instead of underscore P, I will name it underscore A, just to ensure that it's an assertion check. And just remember, the only difference on the way you write concurrent assertion and regular immediate assertion is that in concurrent assertion, in immediate assertion, you will just write assert whatever you want to assert, and that's it. And you could just also add else error system task. But in the concurrent assertions, which checks uh, for the particular sequence concurrently throughout the entire simulation, you just have to assert the property, not asserting directly. So that property, and inside this, you could write the name of the property as, let's say, error, and inside the error, let's say, assertion fail. A and B are same at the same posage of CLK, the clock signal. So this concludes our very simple question, in which both the signals cannot be true at the same time. So let's move on to other question, and this is going to be another simple question, and it is just a series of sequence. And in the second question, what I want when A is true, then on the next clock B should be true. And if that's the case, in which the case is if A is true, then on the next clock B is true, then on the very next clock after B is true, A should not be true, or it should be deasserted. So you could just write this using a very simple sequence. So let's begin. Property, and let's name this property A, B, and not A underscore P. And I want this property, like every other question, to be clock synchronous and to be sampled at the posage of clock. So here A should be true, and you have two options. Either you could use the non-overlapping implication operator, or you could directly use a delay of 1 like this. Here, in this case, let's just use this delay, and you could either thing will work just fine. So if A is true, then on the next clock B should be true. Then on the very next clock, oops, A should be deasserted or not true. So this concludes our next property, and let's assert this with the label. Okay, instead of P it should be A. Else we will get an error. We will just write that property A underscore B underscore fail. So that's it. So it was that simple. Just remember, you need to understand the basics. That what are the differences between the concurrent assertions and the immediate ones. So the concurrent assertions will just keep on running uh, parallelly during the entire simulation check, during the entire simulation run, and also the properties or the sequence are checked, are sampled during the pre-pond region. So you need a brief understanding of the timing regions in system Verilog. The pre-pond region is the very first region, and the other regions such as the active, the inactive, the non-blocking region, and the postpone region comes after that. So the values are sampled in the pre-pond region, which is a little bit before the clock edge, and the checks they happen in the later regions. So you need to just take a note of that, because sometimes you may want to display some values in the assertion, and it will display the different values, the values that you get after the non-blocking region. So that values might be different than the one you sampled. So I might make another video in which I will just focus more on explaining the basics of the sampling and the concurrent assertions. So let's move on to the next example for this video. So in our next example, what I want, there are three signals, A, B, and C. And A, when A is true, then on the next clock or next passage of clock or next cycle, B should be true. And then after that, on the following, when B is true, after A is true, then on the following uh, 0 to 3 clock cycles, then on the following 0 to 3 clock cycles, C should be true. So this basically means that if A is true, then on the next clock cycle, B should be true. Then there is a range that at any clock cycle between 0 or 3, C should be true. So how could we do that? Let's find out. So I will begin with writing my property. And let's name this property A, B, C. Yeah, ABC is going to be a very simple one. So let's name it ABC and underscore P to indicate that it's a property. And I want this property, like every other property, to be sampled at the passage of the clock signal. So let's begin with it. A is true. Then one clock cycle later, B is true. Then the case is that you have to write a range in this way, to hash, and then it states that then on the any clock cycle between 0 to 3 clock cycles, C should be true. C should be true. So this concludes our property. So let's try to understand it technically, what is happening. So what will happen when the sequence A is true? So when the sequence A is true, then there will be a thread. There will be a thread which will detect what is going to happen to the B on the on the next clock cycle. So it will detect on the next clock cycle that whether B is true or not. And if B is not true, then that thread will fail. It will fail, and hence the property will fail, and the check will not happen, of course, because the sequence is not getting it's not getting followed correctly. So there will be a thread which will check that whether B is true or not. Let's call it thread 1, and it checks whether B is true on the next clock cycle or not. So I'm just writing it. So what is happening theoretically? Then what is happening after that? After that, there will be 3 threads. Not 3, 4 threads. There will be one thread. Uh, there will be one thread. Let's call it thread A. On the very same clock cycle. And it will check what is the value of C. And it will check whether C is true or not. So there will be following corresponding threads. So in the same clock cycle, when B is true, a one thread will be created, and it will check whether C is true or not. And right after that clock, uh, let's say in the next clock, that particular thread will be destroyed. And then again, since we have declared a range of 0 to 3, on the next clock tick, there will be another thread. Let's call it thread B. and it will also check for the same thing whether C is true or not. And then again, it will happen again on the next clock, on the 2 clocks later, and let's call it thread C, and it will also check the same thing whether C is true or not. And then finally, since we have declared a range of 0 to 3, so there are 4 possible threads, and the final thread will be checked on the 3rd clock cycle after B is true. So let's say this, and let's call that thread, I'm assuming the name of the thread T, and it will also check. So the reason I mentioned this is just to give you a brief insights of what is happening during the assertion check. And it might not be that important when you are using a small range of 0 to 3. I mean, any modern simulator and any decent computer can take it easily. But for certain ranges, it could be a bit problematic and a performance taking assertion. So I'm just giving you an insight, and you will get it why it is important during our next assertion example. So this is what is happening. So regardless of whether, let's say, if on the same clock cycle C is true, which basically means the thread A is getting passed. So what will happen to the next upcoming thread? Will they still exist or will they get destroyed? No, they will not get destroyed. They will still happen. They will still get checked, and they are independent of the other threads. So because of this range, 4 threads will be triggered right after B is true. So that is how things work under the umbrella of assertions, the concurrent assertions to be specific. So after this, let's just go ahead and let's assert the property. Oh, let's name the label A underscore B underscore C A, assert the property, and the name of the property, which is A underscore B underscore C underscore P. And if the assertion fails, else it will throw up an error, and it should not be S, it should be else. And let's write a simple statement. Assertion failed. And this time let's just write the name of the assertion because it's a long sequence and I don't want to waste the time of the video by writing everything inside the sentence. A. So assertion failed. So this concludes our assertion. So let's move on to the next assertion. And in this assertion, let's try to understand that why it is important to understand the concept of threads during the assertions, and specifically in a case where you are writing a certain range. So this time we will write another property, but this property is going to be different. Everything is going to be same. The only difference is that C can be true any clock. C can be true at the same cycle or any clock cycle after B is true. And of course, and it should take a note that B should be true one clock cycle after A is true. So it is same. Instead, instead of uh, this time, instead of the previous assertion example in which we are mentioning a specific range ranging from 0 to 3, this time C could be true at any clock cycle after B, or it could also be true at the same clock cycle during the B. So let's write the property. B underscore C underscore C underscore any property, and it is going to be a very simple one. So A is true, and one clock cycle after that, uh, B should be true, and then either on the same clock cycle or any clock cycle. So we will use this. So any clock cycle after that, C can be true. So let's try to understand what will happen if C is not true in the, let's say C is true in the 100 clock cycle after that, or C is not true forever. So what will happen? So the same thing is going to happen, but here comes the optimization issue. The thread will keep on generating. So after that, on the fourth clock cycle, there will be another thread, and after that, on the fifth clock cycle, there will be another thread. After that, on the sixth clock cycle, there will be another thread, and after that, it will keep on happening, and so on. So if C is not true for a certain clock, or C is not true forever, so this could put quite a toll on the system, and the threads will keep generating during the entire simulation run. So to tackle that, there is a way which I will discuss on my upcoming videos. But right now, this is what is going to happen inside uh, during the assertion during the simulation run. So the threads will keep on generating. So that's the case for this particular kind of property. So let's just go ahead and assert the property. And the name of the sequence was A underscore B underscore C underscore ANE. And I should put underscore P after this. And it would be very convenient if you put something like this. Suppose if you want to search the properties, you could just write underscore P and you could just iterate through every properties. So this makes the debugging and even the readability very simple, and you are just going to end up saving a lot of time. So also I better label this the assertion check. So let's call it with the similar label, and instead of P I will write A and assert property, and if the property fails, else. If the property fails, let's throw an error. Assertion failed, and let's write the name of the assertion. C any A. So this is that simple. So it is going to just keep on generating the threads, and that will be problematic in some scenario. And there is a special kind of method in assertion which is used to tackle this, and I will just uh, explain that in my upcoming video. But uh, instead of that, let's just use this in this video only, and it is a very simple step. So what I did, I just asserted this property, and what I can do, I could write another property. So yeah, there's a thing. You could embed a property inside another property. So what I will do, I will write another property, and here I will name it almost same. Only difference is that I will be using a certain method which is called as first match. So if you will put any sequence or any property inside the first match, what will happen? You will just end up, suppose, uh, so let's first just write the property. So what this will do, so here I've explained that after when B is asserted, right after when A is asserted, there will be multiple threads that are being generated, and each of these threads will check whether C are true or not. So what first match will do, it will just do it will just go with the optimization, and it will check. Let's say that at the second clock cycle after B is asserted, C is true. Like C is true right here. So what it will do, it will check for all the threads. So thread number 0 is created, thread A is created, and it checked that whether C is 1 or not, and it failed. The C is not 1. Then thread B is created, and it also checks for the same thing, and it fails. Then thread C is created, and it checks. And when C is true in the second two clock cycles after B is true, then what it does, it ends the remainder of the threads. So each of the threads, they will be closed. They will be destroyed. This will be destroyed, and hence this will be destroyed, and this will be destroyed. I mean, it will just never let them happen. So this thread won't be generated. So the very first thread, right after very first thread which passes, the remainder of the threads will not occur. So it just releases the performance stall which is happening in our first case. So it is useful for this scenario in which you are just not limiting uh, the next assertion or next signal to any limited range. So first match helps in this way, and it becomes really important. So this is what first match is doing, and right after that, here instead of writing this, I will write the first match property. So this is what first match will do, and it will just eliminate the need of generating any other property. And yet still, it is essential that you should know about to design that where the C will be generated. And if you did not use the first match, even after C is true in the thread number C, the thread D will be generated, and this should, let's say, thread E, it will be generated, and let's say thread F will be generated, and thread G will be generated. So multiple threads will keep getting generated until the end of the simulation run. So these threads will keep on generating, and just understand how complex this entire scenario is. Let's say this sequence happens again in few clock cycles later, and then that particular sequence will have its own will have its own crowd of multiple threads. So in the end, you will be multiplying lots of threads, and which will take quite of performance toll. For the very same reason, for that reason, we will use first match, and we will just put the property or the sequence inside that first match. And remember, you could just embed a property inside another property. So this will just ensure that if the property is true, then the remainder of the remainder of the threads will not happen. So that's all for this video. This video we discussed some simple assertions which were very simple, and other than that we discussed the range of assertion in which uh, it could happen. The C can be asserted in any clock cycles after B or at the same clock cycle during the B, and we also understood the concept of threat in the assertions, that how threats works, and also we learned the usage of the first match for the assertions. I hope you find this video useful, and please stay tuned for more. Thank you so much.